Shall we start now?
Yes, sir.
Okay, great. Okay, so now we are going to start for PCI related questions, Rajendra.
Okay.
So, how much time you worked on PCI side?
On?
PCI verification, PCI based design verification. How much time you worked?
So it is,
Years wise.
I would say around 8 to 10 years.
Great. Okay. Okay, let's start on PCI side. Okay, so if we say PCI, like as I can see, like you are working on storage company. So do you know the SAS? What it does? Basically, SAS. I mean, stand for SAS in PCI term.
So in the PCI terms, if we talk about SAS, SAS is mainly terms derived from the SATA. And when you talk this PCI terms, the PCI it converted into the NVMe, which is the non-volatile memory express. So there we don't use the SAS term. SAS is used with the SATA, but when it comes to the PCI, it is coming into the NVMe, that is a non-volatile memory express.
Okay. Okay. So in PCI, like there are different generation, like generation 1, 2, 3, 4. So you worked on which gen versions? I mean generation.
So if you see, there is a different generation 1 to 5. Now the generation 4 and 5 are recently one. This is 2.5, 5, 8, 16, 32. So I like in the last project I was working, I was working on the Gen 5 only.
Okay. So in terms of generation like PCI 2 to 3, I mean, what differences you can see in PCI generation side if we move from PCI Gen 2 to 3?
So when you say the Gen 2 speed was 5 gigabit, and then it comes to Gen 3, there is speed is 8 gigabit. From Gen 2 to Gen 3, there are major changes in the transaction layer. And when you see the transaction layer, there is a more packet introduced. Like if you see atomic operation, fetch, add, cache, swap, and all these things are added over there. And when it comes to the physical layer, if you see the 8-bit, 10-bit encoding used to be there. Now they move to the 128 and 130-bit encoding. There are more changes like in the data link layer. I think data link layer, the changes happened in the credit wise where the scaling things came into the picture, and ordered set, there is also a change. Like earlier there used to be the there was no EIEOS, electrical idle exit order set. From Gen 3 onwards it is introduced, which helps in doing the block alignment.
So what is the difference?
Many changes. Yeah, please.
Yeah. So if you say like electrical idle order set and electrical idle exit order set, what is the difference between two order sets?
So when you say electrical idle ordered set is the one which device says that it is going into the electrical idle before transmitting to electrical idle. So when it comes to the electrical idle exit order set, electrical idle exit order set is the main set which is used for the Gen 3, 128 and 130-bit encoding. This is the main set which is used for the block alignment, where it does like if you see in 8-bit, 10-bit, we do the bit lock and all this. And there it is the starting of the block alignment. Once this packet comes, the device is in the locked phase. Second thing is, let's say you are in the L0 state. So you want to come out of the you want the the other part of the link wants the device wants the other transmitter to be out of that. So what does it do is electrical idle exit order set it sends. So if you see from the name itself, you can say electrical idle exit order set is there. So it is coming out of the electrical idle.
So basic thing, like if we say electrical idle, I mean in PCI, I mean lane or link. So we call electrical idle. What it does, electrical idle, I mean.
So electrical idle is the voltage level of the signal. It is less than 20 millivolt. So electrical idle, if you see, that is not. It's kind of the high G state, not the actual high G state. So when the device is electrical idle, both the device will be having the same polarity, and there would be less than 20 millivolt.
And what it does, a DC common voltage? I mean, both are same electrical and DC common voltage.
Yeah, DC common voltage will be there.
Hmm.
So DC common voltage will come. What actually DC common voltage helps is DC common voltage helps you detect that there is some device present on the link.
Okay. Okay. So let's start discussion on this LTSS, and maybe about this LTSS machine. So can you just give me name like all major state machine in this LTSS system?
So if you see in the basic LTSS state machine is
Hey,
detect,
hey,
calling.
sorry, I want to jump in this. Rajendra, what is the difference between this electrical idle and logical idle? Can you explain?
Okay, so right. So electrical idle, like I mentioned about this one, the voltage levels. But when you say the logical idle is again there would be a this will be data following. This is kind of the data going on the bus, and that is a 0 0. So if you see that when the data is going over there, it will be greater than when I say electrical idle, it is less than 20 millivolt. The difference between the voltage. But when it comes to the logical idle, that would be the logical value on the signals. That would be 0. And in that case, the difference between D plus and D minus, it would be greater than 20 millivolt.
Okay, okay. Thanks.
So where exactly use this logical idle, Rajendra?
So logical idle is kind of thing. Let's say you logical idle when you don't have any packet, and when you don't have any kind of the packet, that time you used to send the logical idle so that the bus does not get into the low power states. When you say the low power state means L0S.
So if there's a no packet, I guess it will be entering in this L0S, right?
So it will be
After some
right.
time
It will be
frame.
going into yes. So so if you see L0S entry and exit happens with some cost of the latency, it's a 50 microsecond something, right? So if you don't want the other part in the low power state, means you do for the 50 microsecond also, then you want to keep the link alive, right? So to keep the link alive, what you do is you float the logical idle.
Okay. Okay. So both transmitter and receiver both are in the logical idle, or somewhere like one side would be in in the electrical idle, other one is
logical idle signals are symbols are sent when you want to keep the link active. So if my understanding is correct, it is related to the L0S. Now L0S is a transmitter specific, and RX it is independent.
Okay.
And these are the two entities of the different end. So it is up to the both the ends how do they want. It doesn't mean that logical idle on one side will be getting the logical idle on the other side also.
So if we say L0S, okay, we started discussion on L0S. So is there any condition or any constraint like a transmitter? Will start this entering in L0S initiated from transmitter side, receiver side, or
No.
can be
It's
initiated
nothing
from
like
both sides?
no. L0S is nothing like that. L0S can be initiated from any side, and it is only for the transmitter. So it is from the, like if you talk about the RC side, RC can initiate the L0S whenever it feels that it doesn't have any packet to transmit.
Mm-hmm.
And same thing with the other side of the transmitter.
Okay. Okay, I'm coming back on this LTSSM state machine. So, what are the major states actually in this LTSSM?
So detect state, calling, configuration, and L0. These are the, if you see, these are the main state which are taking, which the link is going through. Across other than this, there is hot reset, recovery, L1, L2. These are the different states. L1 and L2 is kind of the power saving states.
Power states.
Hot reset is kind of the where you want link, and there is a disabled state where you want to keep the link disabled. And there is one more state I'm forgetting: hot reset, disable, loop back, where you want to do some kind of the testing.
So about this detect state machine, what what it does basically, purpose of this detect what happened in this particular state of this artificial machine.
So when you talk about the detect state, this is the only state where the RC and DP comes to know that there is something present on the link.
How?
So what it does is actually, the common voltage, right? So it varies the common voltage and see the charging, because whenever new device is connected, so new device is connected and it will add some load on the bus. So what the RC and EP does is they vary this common voltage and they see the loading effect on this ramping of the voltage. With this, they come to know whether the device is present or not. So what they do is detect quiet and detect active. So in that case, you will get a voltage greater than 20 millivolt in this case.
Okay.
Or in other word, if I say in one line, it is kind of the detecting whether something is present on the link or not.
Before that, what would be the state between? What would be the link state? There's a in case
Detect quiet.
detect. So what would be? It would be electrical idle, and what kind of state? If we say in
So
one device to other device.
you can say it is electrical idle because it is the voltage would be less than 20 millivolt.
Okay.
And there won't be any common voltage at all.
Okay. So next is the polling, right? In polling, what it does.
So if you see polling, when it comes to the polling, there is exchange of the TS1 and TS2 happens. There is you need to do the bit lock, symbol lock, polarity inversion, and rate exchange and FTS establishment. These things happen over this polling state. And if there is some link, some lane is not working, that time it goes to the polling.compliance. So it is like 1024T.
1 second. This lane and link with all those things you are saying, it is defining in this polling state.
No. They are not defined. It is just checking what all lanes are active. Here it does the bit lock and symbol lock and polarity inversion. So in this case, here there is no, if you see the link negotiation and the lane negotiation doesn't happen in this. It happened during the configuration phase.
So where in the state of this? Okay.
During the configuration phase in the TS1, it sends the link number and the lane number.
Okay. So during this detect and polling, in polling, what would be the state of this link and lane with lane width and link width details?
So if you see, during the TS1, there would be a pad. There would be a padding. There would be kind of a pad. Pad is kind of the one kind of the kind of the encoding that we use for this symbol. So there it would be the pad symbols, which will be there in the polling state. When it goes to configuration link width, lane width, there it will be sending the actual link width and lane number.
Okay, so in configuration mode state, basically you are saying our lane and link, all those things define, negotiate between transmitter and receiver. Yeah. And based on that, define. So in case of, suppose, there's a lane reversal, how it handle, in this state machine? How it will make sure that it is,
So when you say the lane reversal, so what happens is if you see TS1 and the TS2. So TS1 is kind of packet where the information is there. TS2 is kind of the acknowledgement. So what happens is in the TS1, both the device, there is a lane number, lane number it would be sending. So that way it comes to know whether it is like 0, from let's say one device send the 0, 1, 2, 3. So on the same lane they would be checking what is the value of the TS1 received from the other part of the link. So that way it will come to know whether it is a 0 to 0 connection or 0 to 3 connection. So that time what does it do? It's the EP responsibility who does the lane reversal.
So in case, suppose there are 4 lane, right? X4. Okay, in that for third one, it is not responding basically, the lane basically, it is always sending pad. whereas fourth lane is passing all lane details properly. So in that case, what will happen? Will it be X2 or
So
X4
wait,
or
no.
X3?
So it will be cross 2 only when, because it is cross 1, cross 2 or cross 4. It's not like that you can do the skipping of the lanes. So if it is not detecting the third lane, it will skip that, and it will skip any lanes further on that. So link will be working in cross 2 only.
So I mean, fourth lane will be discarded. You mean to say?
Yes, fourth lane packet will, but it will be in the electrical idle state.
Electrical item. Okay. Okay. So now I'm coming on this power state L1, L2, L3. So exactly what it happened like in the L1 power state,
So okay. So when
and
it
who
comes to the
initiate
power,
that? Yeah.
so okay. So when it comes to the power state, so these power states are mainly for saving the power. And when it comes to the saving the power, ultimately what you need to do is you need to turn off the clocks. You need to reduce the frequency. So when it is in the L1 state, so there is a core logic. So core means max state. So max will be completely turned off, but there will be the 5 will be turned on in the L1 state. Now L1 when it is turned on means it will be receiver detection would be enabled, but the transmitter would be the high impedance state. Now there is L1 is further subcategorized to L1.1 and L1.2. This is again is done so as to save more power. When it comes to L1.1, and these states are like a mutually exclusive. From L1 it can go to L1.1 as well as L1.2. So it depends on the implementation, how the design is implemented. So when it comes to L1.1, here the PLL is 5 PLL is also turned off. So the 5 PLL is turned off, but again the receiver detection, that common mode voltage, that will be present. But in L1.2, that also will be turned off.
So if I talk about this L1 power state, who initiate? Can you explain me the negotiation from between transmitter and receiver? I mean, based on
what happens is it can be initiated by anything. So one is the ASPM, that is active state power management, another is a power management software, active power management software. So when it comes to the ASPM, that RC side, so RC side jump into the picture, and RC sends a DL packet, enter L1 or enter L2 kind of the packet, DL packet, DL or it's enter DL, yes. So RC sends the packet, DL packet, and which comes to the EP, and once EP acknowledge that yes, you can go to the low power, it sends the ACT packet, and accordingly then it will start sending start initiating the process, that is sending the electrical idle set before going into electrical idle. Now the EP side, because it already acknowledged, so it will start shutting down its MAC, shutting down its clock, and that way it also sends the electrical idle at the end.
No, acknowledge means other side.
If you see,
what kind of acknowledgement is passed to the transmitter so that
if
it will take as acknowledgement.
there is a PM request, DL packet is there, PM request L1 entry something. DLLP packet is there, and correspondingly PM request L1 ACK something. So the device also indicate that now it can go to the L1. But if their device may reject that request by saying NAC. So in that case, this request like is the RC initiated. Okay. Now it comes to the device initiated. When the device goes to the D0, D1, and D3 state. So now it's a device initiated. Now device requests the link by going into the L1 or L0.
Okay.
So there are, like, if you see, there are two things. One is state power management, another is active state power management. So one means both the things has a separate capacity controlling resistor, and they has to be, this can be done by the RC as well as EP.
Okay. So if I say like endpoint side, like um, it will not be initiate like to enter in the power state, like any of the power state. It cannot be initiated from this endpoint, or always
So
initiate from. I mean, it should start from RC side.
so if you see from the RC side, it will get the RC side. So these are the two. You think it as like the two-person RC and endpoint, RC and EP. Now they both can go initiate the low power request. Okay. Now when it is initiated by the RC can send PM request L1, PM request L2, 3 something. So if you see the DLP, there are packets are there, right? So those packets will be sent by the RC.
One thing, this PM request L1, you are saying like what it does basically, packet
So
or
it
is
so it is a packet sent by the RC.
okay? It's a request
So
going to
this
the receiver, you are saying, and after that,
yes.
packet form, it will
So
go to receiver. Yeah, okay.
so it will go to the EP. Now EP it
Hmm.
is asking, I want to save the power. Can you go to the low power?
Hmm.
So what the device does is device sends the corresponding ACK or MAC. When it says
Correct.
ACK, okay, I can go to the low power.
Hmm.
Then it what it does is then it starts processing, like it like core side, it puts the device into the low power, and it then turns off the Mac, then it turns off the clock and all this external clock and all this, and it says like now I'm ready to go to the low power. Then it sends the electrical idle.
Okay.
Means it will go to the L0. It will go to the L1 where it sends the TS1 packets and all this. Not
Hmm.
TS1, something, some communication happens where the device indicate, yes, I'm ready, I'm going into the L1 state.
Yeah, PM request.
And that
Yeah, L1.
PM request ACK is going from the, it is going from the
Device.
RC.
No, PM request ACK will be coming from device, and request will be coming from RC side in under ASPM.
Right. So that RC will be sending that, right?
So these are the what kind of packet? It's a DLP packet or TLP packets, or what kind of packet this?
It's a DLLP packet.
Okay. 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 So you're saying after that, like after getting this acknowledgement from receiver side, it will enter in the DLP, and before that, it will serve all packets. Like what are the packets are pending, it will,
Yes.
and after
Yes.
that, it
So
will send the
it will
acknowledgement.
yes.
Hmm.
Yes. After once it is processing like backend, if you see the front end in the storage, there is a front end and the back end. So there
Hmm.
might be the packet processing going in the back end. So once all the backend processing is done, that time it will acknowledge.
So this is for entry. And what about exit?
Hmm.
How it will come out from L1 power state? Power state.
When you say the L1 exit, from the L1 it will go to the recovery. And when it say the recovery, from the recovery, just 1 minute, let me think over that. It has to be woke up, and it will go to the recovery and electrical exit order set. Okay, so so it can be initiated when it comes to the substate from the substate it use the clock rec signal, that is like out of band signal.
But clock rec would be
And
in substate L1.1 or L1.2 substate, like clock rec.
right, right.
In L1 case, I mean, this is
In
also.
L1 state where, okay, what does it do is whenever any, let's say any device wants to come out of that, what does it do is it enables the transmitter. So transmitter send the TS1 packet. So it will once it says the TS1 packet, it will go to the recovery.
So what exactly it will pass in TS1 packet? I mean,
TS1 packet, what exactly it will
I mean,
question? No, 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 no. I think it's not a TS1. It's a electrical idle exit order set something it sends. It's not. It cannot send the TS1 because the link is not active. It will send the elite because it is electrical idle. The link is in the electrical idle, and electrical idle which is there. It brings the detect. Okay, recovery. So I think what happens is whenever it's say when the device wants to bring the any side want to come out of the L1, it sends the electrical. It takes the it floats the signal out of electrical idle, means greater than 20 millivolt. Once it does that, it sends the like other side also comes to know that okay. So what happens is when it let's say EP wants to come out of that. So EP, what does it do is it will take out its transmitter out of the electrical idle. Means it will float the float the voltage greater than common voltage, that is 20 millivolt. So the other side comes to know that this device is trying to bring up that. So that way, but after that, the initiating device sends the TS1 packet, electrical idle exit order set. So other side comes to know, like I got electrical idle exit order set. That is kind of the confirmation that it wants to move out. So once it does, this device sends the TS1 packet.
Right.
Once it gets the TS1 packet, then it goes to the recovery state. So in that TS1 packet, there is it's a standard packet what it will be sending the whatever the lane number, link number, that will be the standard format. During the while it is using the polling and configuration state, it won't be pad number, but it will be a proper number. So once it go to the now it will go to the recovery, and then after that it's a state machine will take care of that.
Okay, fine. Okay, so there's a state, substate also, there power state. Exactly who initiate and how to enter in this L1.1 or L1.2.
So if you see this L1, this can be initiated by anything, but before that there is a capability exchange information. But RC reads that capability register, that is L1 substate register and L2 substate register, and it comes to know whether these states are spotted or not. So after that, what they use is they use the out of band signal, that is a clock rec signal. So clock rec, based on the clock rec signal, whether it is asserted or deasserted, they make the call which state they want to go.
So okay, what I understand here, like in the L1.1, L1.2 substate, you are saying check the capability. Okay.
No. Hold on. So these capabilities are exchanged during the animation phase itself. So animation phase, they come to know the other end is what the other end is capable of.
This substate also it will check during enumeration time. I mean,
yes.
Exactly yes. How?
So this is a configuration register. You can read the configuration space.
Okay. But okay, fine. So you are saying enumeration time, it will check the capability, and after that, for entering in this L1.1, L1.2, it will any register needs to be configured. Which one, or it will go for both L1.1 and L1.2 substate?
No. So it is either of this. So you need to enable that. So this will be enabled by the RC or enabled by the device software, device firmware. So accordingly, it will take the call whether it can go into the L1 or L1.1 or L1.2.
But initiate initiation taken from RC side or EP side? I mean, what I'm asking, transmitter or RC will only initiate, or you're saying endpoint or can also initiate to enter in?
Yes, it can be initiated from EP also, because once you into the L1 state, then it comes to the clock rec signal, and clock rec is the out of the band signal. So what the initiator has to do is, initiator has to float this clock rec signal. Means it has to observe this clock rec signal. So in case it wants to drive that, so it has to float that signal. Float means from its side it need not to drive that. Now other side will keep observing this signal. Now it comes to know that this signal is floating. Means strength is reduced for that signal. So once the strength is reduced to that signal, it gets the indication the other side wants to go further power saving mode. So based on that, what it does is it also starts processing that. So once it starts processing, then after that it deassert the clock rec signal.
Okay. We need to check again, because what I think, like root complex or RC can only initiate to enter in this L1.1 or L1.2 substate. I mean, EP cannot initiate to enter in this substate.
My understanding says that because this is a clock rec signal, this is out of band signal, it doesn't depend on the protocol. So even anybody can initiate that one.
Okay.
It's
So
not a protocol specific.
okay, fine. We'll check that. Okay, for this understanding. What I understand, like RC can only initiate this L1.1, L1.2 substate to enter. So exactly how it will, I mean, what are the states basically for entering in this substate power state, I mean L1.1 or L1.2? It's just clock we need to basically drive and to enter in this L1.1 or L1.2.
Yes, so your device should be L1 capable, like there's a active, there's a state capability, like whether your device support L1 or not. So that capability has to be supported. Once in L1, then you just need to see the clock rec signal.
And how to exit this? And there's L1.1 zero idle and L1.1 entry kind of
So
states, right?
right.
Substates.
So these are the substates where it's kind of the transition. So when you say the transition means it is because this is the hardware, right? You can go step by step. So these are the different steps mentioned over there. Like and in L1.0, you do some kind of like some steps. Exactly that steps even I don't remember. And L1 dot whatever you're talking L1.0 idle is kind of the L1 state in the previous generation. Now L1 0, L1 entry, L1 idle, L1.1 state. These are the substates. So L1.1 is the final state where it lands up, and whatever I'm talking about, that PLL would be off, common mode voltage would be off. All these things would be actively working in L1 dot entry. L1 dot L1 dot sorry L1 dot idle, L1 dot 1. In L1 dot entry, it is a kind of the preparation for doing that.
What kind of preparation?
So when you say you are turning off the clocks and all these things, right? So you need to take care of the logistic surrounding, so logistic for the surrounding logic.
Okay. So
So that details even I didn't go into the details, but we can refer the specification.
perfect. So for verifying this, I hope like you verified all those power states. So how did you verify this whether it is L1.1 or L1.2? I mean, do you have written any monitor, any checker, or any person for that?
See, when it comes to the this L1 script, we have the checker because this is a third party IP. So third party IP, we are not bothered about the whatever internals of the PCI protocols, but for sure we are bothered about the logic surrounding that PCI. That is our DOT. So we are ensuring that when we are going to that state, we are checking that clocks, whether the proper clock is there, or whether that part of the logic is off or not. And in other words, in our design, what we were checking is we were checking there was a register which is indicating that the design is in the backend is in the low power mode. So we used to read that register, and we are okay with that.
So
And when it comes,
did you check the clocks? I mean, whether clock are getting gated or not?
see, we can do that, but I'm saying that we have the register indicating that its device has entered the L1, L0, L1 means D2 and D3 states. So that register indicates that D3 state has entered.
D2, D3 state. I mean, device state. You are saying?
Yes. So link state is linked to the device D2 and D3. D0 is active state. D1 and D2, these are the different device substrate based, and device substrates are mapped to the link state. And
So
I think D2 and D3
yeah.
are mapped to one link.
So exactly D1, D2, D3, you are using for entering in this L1 or L1.1. I mean, exactly what is the purpose of D0, D1, D2, D3? I mean, you
So
are
D0, so if you talk this link terminology coming from the PCI side, and device 0, D0, D1, D2, D3, these states are coming from the hardware logic sitting around this PCI link. So it is related to the device where the PCI is incorporated. So when the device is not in D0, that is kind of the low power state. And when the number increases, the power state further reduces. It is up to the implementation what you map D1 to. You can map D1 to L1. You can map D1 to D2 to like L2. These kind of the mapping. This is a design specific implementation.
okay. So as you said, like L2, can you just help me to know the L2 entry or exit?
L2 is kind of the lowest power state. So it is like once you go to the L1, then it will go further down into that. So entry wise, when you exit wise, I know there is a kind of auxiliary beacon signal. There is a low power, like low frequency signal, sideband signal, which you use to go you to exit from the L2. But entry wise, L0, L1, and L2. I think it is going from okay. So if you see ASPM, there is a packet and PM enter L1, L2. These kind of the packets are there. So using that, you can go to the L2.
Okay, PM enter L1, PM request L1. I mean, what is the PME turn off all those things, messages? Exactly.
PME turn off message. Yeah, there are some kind of messages also there. If I'm forgetting that, what is the PME message? Power management messages are there, but these are related to the power management only. But I need to go into
PM underscore enter L23, DLLP, all those things basically used for L2.
These are the DLP, but there are power management messages also. If you talk about the message.
But PME turn off all those messages and PM enter L23 all are the DLLP which are using for entering this into L2. Okay. Okay, this is a power state. Next was. In Gen 3, equalization we use, right, which is the additional thing in this. Exactly what is the purpose of this equalization?
So equalization, if you talk, is kind of the telecommunication terms where you would be doing the emphasizing and de-emphasizing. Like you would be passing some kind of the RC circuit, like filters you would be using. What I would say, because of the high frequency. So what happens is high frequency is there. So when you are sending the continuously one on the bus, so because of the continuous one, because of the capacitance effect, when you want to send, let's say after 5-1, you want to send a 0. Because of the capacitance effect, what happens is that 0 is not properly reflected on the receiver. It will be having the problem because of the because of this continuous one. The other side capacitance would be charged, and when it sends the 0, it doesn't go to the exactly 0 level. So, and it's a high frequency. When it's coming to high frequency, if you see the equalization coming into the picture, 16 gigabit, 32 gigabit, and all these things. So that time we make the advantage of this. What we do is, it is whatever the channel response. So this is kind of the this kind of characteristics, and that characteristics is done by the companies and their labs, where they figure out what is the response of the channel for the correspondingly PCA protocol. So what they figure out this kind of the filter parameters to be exactly filter parameters they configure, and it's high frequency component. This is what I remember for the equalization.
Okay. And there's an additional like LTR, I mean, which is using some word in Gen 3. It does basically LTR.
So LTR is kind of again the power saving mode, and this is kind of latency tolerance reporting. So it is indication by the device to the host that this much tolerance, this much like I can wait this much time when you are in power down mode. So after this much time, I certainly need the response. So what happens is when the RC, because it is having the multiple endpoints, so that time it comes to know, okay, this device can wait for 100 millisecond, other device can wait for 50 millisecond, and other device can wait for 60 millisecond. So I need to at least at least a 50 millisecond I have the time to go into the low power mode. So that is the way it makes use of the LTR. So LTR message has to go periodically from the device side to the RC to indicate that how much exit latency it can tolerate.
Can it be adjustable or configurable?
Yeah, it's a configurable. So it's a device dependent. So device depending upon the logic it is working on, it can set the value.
Okay. So there are some device state actually D3 hot, D3 cold. Exactly what is the difference and purpose of these two substates, D3 hot and D3
So
cold?
again, I would say these are the again these are the these are again power states, and it's the device implementation specific. So D3 hot and D3 cold, when you say, it's kind of the wind power, V power okay. There is kind of the power okay in every design where they say power is stable or not. When you say the D3 hot, you are not playing with the power button. But when you say the cold, you are turning off the complete power.
So in which power state it will come, D3 hot or D3 cold?
D3 is very much low. It's the device would be in the low link, PCI link would be in the L2 state.
L2 state, okay. And what are the, changes happen in the design in case of D3 hot or D3 cold? Any change difference between D3 hot and D3 cold in
So again, I would say
inside?
this is again the design dependent, design implementation dependent. So in my design, like we were having the D1, D2 and D3, D1 and D2 state. We were not even having the D3 state, where the D1 and D2 state were linked with the L1 and L2 state something. So again, I would reiterate that this is the again the design implementation. So it is up to you what you want to do. But the main difference D3, as per the definition, D3 hot, where the you would be having some power. The power OK button would not be turned off. But when it is the cold, it would be turned off. You would be
Because
playing with the power. You will be turning off the power off. Power also.
because D3 hot and cold, these are the standard basically PCI specific word basically, and those are using for
Uh,
L2, L3, right? Specifically power
Yes.
states.
So yes, you are talking about now there is a two things. One is the device state and another is the link state. So
Hmm.
this device state is related to the where the PCI device is incorporated. It's related to that device.
Hmm.
And when you say a link state is a PCI standard.
Okay. Okay, so in during your verification, exactly in the design, what are the components available in the design and PCI specific design? What
So
are the
PCI
components were
specific.
there?
So we like in our design we were having the standard components where we have the PCI was there, then it was having the host interface module like HNVMe, which was incorporating HNVMe, and then HNVMe related protocol like buffering, buffer
No,
management,
no,
which
that's
was
I guess those are parts of like your internal design. I'm asking PCI
uh-huh.
specific. What are the components are there in your design?
Okay, then we have the VIP. We have the LTSSM state checker, which will be monitoring the states. And because we have the VIP, which are delivered from the third party, that is having all the components, which will be having the like monitoring the bus protocols. When bus protocols, it will be like a TL checker, PL, DL, all these checkers were there. And
No,
then we have the
in your design, right? There are
Mhm.
different layer wise. There are would be RTL, right? I mean, what are kind
So
of
if you're talking the layer wise, if you're talking the PCI internal structure, you want to know?
yeah.
So PCI internal structure, like you would be having the PIE, then it will be having the pipe, which would be talking with the MAC, and the MAC would be divided into the TL, DL, and the physical layer. And the TL would
So
be like,
So to handle all those things in your design, I mean, there are different components like Mac, Phi, pipe, all those things are, or each layer wise you had different modules. I mean, Mac, what kind
so
of layers handling in the Mac design?
so Mac will be like it would be handling the logical digital portion of the digital logic of the file, like LTSSM, and it would be like handling this TL, DL handling, transaction layer, data link layer, all this handling. And when it
Hmm.
comes to the data link layer, it will be handling the power management, flow control credit, and this init FCs, and transaction layer is handling for responsible for handling the TLPs.
So basically, Mac is handling all TL, DL, and LTSS, all related logics are
digital
in this
logic, right?
digital,
Right,
and
right.
phi is a different basically component in your design,
Phi
right?
is a different component which will be mainly responsible for like serial to digital, serial like encoding, decoding, serial deserializing, this kind of thing.
Got it. So pipe actually, what is the frequency of this pipe frequency? I mean,
Exactly, I don't remember. It is pi because this even width I because this keep changing. Somewhere, let me recall, 100 megahertz is the clock that we give. Then after that, internally it is taken, and then it is changed to some other frequency.
so
But if you see,
is there any basically,
hmm,
I mean, dependency from max side clock like core clock, all those things, right? And
see,
pipe clock.
ultimately, what you need to do is see. Ultimately, you have to deliver the frequency what the protocol says. So if you have that
Hmm.
number of the lanes, let's say you have the number of lanes, 4 lanes, and all these are working on this one. Let's say 2.5 gigahertz. That is a Gen 1. So 2.5 Gbps. So accordingly, you need to because pipe is a parallel data. Pipe is the parallel interface which gives the parallel data converted into the serial interface. Now this parallel data has to come at the speed that is like not giving the underrun kind of thing to the serial interface. So if it now the pipe has a different variants like 8-bit, 16-bit, 32-bit, but generally nowadays it is a 32-bit we are using. So you can calculate the frequency in relation to that. So you can see 2.5 GB into one lane, and then you see the pipe width what is available on that. Accordingly, the number of lanes and the data width will be changing, and the core clock will be different. That is running on the max side. That clock will be different.
Okay. Okay, fine. So, and what about the error scenarios? Like, have you coded any error scenarios in your verification, PCI verification? What kind of
So
errors we can inject, I mean, in our
So
verification?
there are you can have different errors. If you see, you have the skip symbols, right? Skip symbol has to come at a particular interval, like 1 1 1 5 3. Like it has to occur at that one. So you can miss those things. But our case, like most of the things, we were injecting the error in the TLPs, where the ECRC error, uh, data width, and all this mismatch, and those things we encountered. Physical layer we encountered some errors, and accordingly we need to inject that, like skew related issues. We need to inject the skews in our design. From the RC side, we have to inject the skew, like give the jitter to test our design. But we
Is
can,
it?
like in the protocol wise, yeah.
Yeah, yeah, no problem. Yeah, go ahead.
So if you see in the protocol wise, there are multiple errors: physical layer error, data link layer error, and TLP errors. So you can see, you can check the design, like PCA design itself. There are like whole lot of and there, like you can have the init flow control sequence. You can change the sequence and see the design behavior. You can give the credit values. You can violate the credit minimum credit values. You can send the packet when you don't have the credit. You can see the device response. So, and there are like transaction layer malformed error, bad TM, nullified TLP error. There are different scenarios out there.
So if I take this ECRC error, how you
Hmm.
had verified ECRC error basically? I mean,
So
I just want
ECRC
method.
error, but we did
Hmm.
ECRC error, what we did is we changed the ECRC value, and from the like in the VIP we were in the VIP we were having VIP was given by the VIP was giving the callback, so we use the callback, and then we driven the wrong ECRC.
And there's some address error, right? Have you also coded this address scenario
So
in
address error like aligned
TLP?
FDW, like FDW byte aligned error, these kind of things. Yeah, this you can do that, but in our case, that I did not do that. I think this was already existing, but we can use a callback to introduce these kind of errors.
So during verification side, what are the exactly any I mean kind of issue you found during your verification? Exactly any of the scenario? Can you explain here what kind of issue, major issue you found, and that was a hitting to your project. Can you explain?
So yeah,
Single. Yeah.
so in GLS we were facing the issue. So what happened is when the GLS came, there was a the synthesis team add the buffer in the PCI path. Because of that, what was happening is uh, the device, the EP was receiving the packet, and there was so much skew, and because of that skew, the lane was getting because of the skew, the symbol was interpret as a like, interpret as a idle. So idle means like the absence of the signal B plus and D minus. That was interpreted as an electrical idle. As a result, the link was getting up only on the one lane. So this was the one issue that we figured out in the net list. There are other issues. There are the other issues. Hello.
Yeah, I'm listening.
Hello. Yeah.
Hello?
There are the other issues. Yeah. Other issue one I remember. So what was happening is because of this jitter only, the link was getting into the recovery, and it was recovering automatically. And this was this was happening like once in a while. And the team was not able to. Team was struggling to figure out where was the issue. So there we figured out that it is a jitter issue, and this was a modeling issue from the IP provider.
Oh. Okay. So, okay, there's a one configuration, right? I mean, type 0, type 1. Exactly what it does, basically, type 0, type 1 configurations, and what are applicable for our RC or EP or switches?
So this type 1 configuration is for the RC kind of thing, RC switches. So type 1 configuration is one. It's kind of the for the intermediary device, for the endpoint where ultimately where it is finally going to land and update the register. There we need the EP0 configuration.
Okay.
Configuration 0, right? Configure 1 0, right?
Type 0.
So that time we use that, yeah.
Okay. Last question, just want to know exactly enumeration. Basically, we do it happen before link up or after link up enumeration.
So if you see, enumeration consists of the configuration packet, and configuration packet can only be sent of any TLP, means any TLP can be sent when the link is up. So this enumeration has to be after the link up only.
What happened basically under enumeration step? Exactly what
exactly it does is it goes and read the initial configuration space. If you see device type and device version, it reads. So what it does is it sends the configuration transaction like bus number, device number, and the function number. It detects how many endpoints are presented, and in each endpoint, how many functions are there, and how many like whether there is any switch on the bus, whether there is any bridge on the bus. It's kind of figuring out who all are connected to me and what are their capabilities.
Perfect. Okay. So interrupt wise, like what kind of interrupts you verified in your PCI verification? You checked both kind of interrupt.
So this interrupt, like it has inbuilt interrupts like a message signal interrupt, where you can send the messages, TLP messages, to give the interrupts. And there is a like to cater the legacy stuff. We have in assert int A, assert int B. These kind of messages are there, so we can make use of that also.
So interrupt is posted or non-posted messaging interrupt.
So this message is kind of this is a posted transactions.
Okay. It's a posted, you're saying, right?
Yes.
Okay. And interrupt acts, all those things. I mean, this is also kind of messaging, posted message.
Yeah. So these are messages. All messages are the posted messages. So this message signal interrupt is the write transaction. This is again the posted transaction. And this assert in text. These are the messages. These are the posted transactions.
Okay. Yeah, I guess I'm done. Anything you want to discuss? Because I have asked like whatever question I had from PCI related, and
Nothing from my side.
okay, okay. Then Amit, do you have any query? I mean, you want to discuss anything from Rajinder?
No, nothing from my side.
Okay. Okay, Rajinder. Thank you very much. Thank you very much.
Okay, sir.
Okay. I'm stopping. Yes.
Okay, thank you. Bye.
Bye bye.
Bye bye.